we are going to well, this one, I guess, yeah. Calculate the internal loads. And then it says, okay, we just have to sort of think through where the biggest problem with stress is going to be. So I'm going to calculate the internal loads as a function of x. And then it's a circular cross section. Bless you. So we are, so we can only calculate, well, we can only do it along the neutral axis. Okay, well, let's see. So the first thing we have to do is calculate the external loads. This thing is 1.5 meters long.
It's a convenient length.
Yeah, that's true. This is R. We have an MR. This is 10,000 times 1.5 divided by 2, so 15,000, so 7,500. And that's everything. So Newton's second law says Rx, Ry plus 0, negative 7,500 is equal to zeros. So Rx is 0, Ry is 7,500. Moment equation, I'll do it about this point. So we have Mr. Then this is a clockwise rotation, so minus 2/3 of 1.5 is 1, so the moment arm is 1, 7,500. So Mr is equal to 7,500. And now we can do the cut. This is for x's from 0 to 1.5. We have an upward force of 7,500, a couple of 7,500, this triangular distributed load doesn't go all the way up to 10,000 anymore because we're only doing, part of this beam. And so we have to think of the function for this line. And that line, we can use these values. The slope is going to be a rise of 10,000 over a run of 1.5. So that...
15,000.
What?
It's 15,000. Really?
No.
No, it's the
opposite.
Of that.
So 10 divided by 1 is like 6 point...
Well, it's 10 to be 10 times 6.6.
6.6 repeating.
So it's, yeah,
6,000.
So this is 6,000.
6,666.6 repeating.
Okay.
nice math.
The slope of the beast. And then T, V, M.
Love that open The slope of the beast.
And now,
National rock band ABC.
so we have 0, 7,500, plus, oh, I'm kind of getting ahead of myself here.
Do we have to find like the magnitude?
We do. So this length is x. This height is 6666.6 x. The centroid is this. And this distance is 2x over 3. And the area is x times 6666.6 x over 2. So that's 3333.3 repeating x squared. So I'll redraw that free body diagram. That downward force is 3333.3 repeating x squared. T, V, M. Newton's second law says 0, 7,500 plus 0, negative 3333.3 repeating x squared plus T, negative V is equal to zeros. So T is equal to 0, V is equal to negative 3333.3 x squared plus 7,500. And then the moment equation about the z-axis, there's no torques in this, so we're not going to do it about x. We have 7,500. That is a clockwise rotation from that distributed load force. The moment arm is 2x over 3. The force is 3333.3 repeating x squared plus m minus vx is equal to 0. So m is equal to vx plus 2222.2 repeating x cubed minus 7,500 now put in x times what we have for v, and you get m is equal to negative 1111.1 repeating x cubed plus 7,500 x minus 7,500. Do the checks. Dm dx is equal to v. dv dx, negative dv dx is 6666.6 x, which is our distributed load function. So that all works. So now we have to think about where these are big, where these are small, because we have to sort of locate a point along this beam where we're concerned about things. So let's draw out these graphs. T doesn't come into anything. V is going to be V is going to be 7,500 here and it's going to be 0 at the end, and it's going to be concave down, so it's a parabola like that. And then the bending moment so that is going to be negative 7,500 here. And it's going to be 0 here. And that is, bless you. Okay, so that is going to be concave this way. Okay, so those are what those functions look like. Which says we're most concerned about stuff at the wall. That's where the shear force is going to be big. That's where the bending moment is going to be big.
Can we only get one or the other here though? Because for V, because this is a circular.
Yes, perfect. Yes, you're exactly right. That's exactly. Okay. So, there's two things we can do. We can calculate the stress due to the shear force at the neutral axis. And remember, the definition of the neutral axis is that the stress due to the bending moment is 0. That's why the neutral axis is an important thing. And we can calculate the stress due to the bending moment at the top or bottom. We expect this to be smaller. It's usually around 0 at the top and the bottom, but we don't know that for a circular cross-section. We can't do it anywhere else. Well, we could calculate the bending moment anywhere else, but these are really the two things that we want to look at. You know, that's kind of all we can do.
It's a major bummer.
Yeah, really sucks. But at the neutral axis, let's calculate the stress due to shear force. Well, sigma tau, xy is equal to negative VQ over IB. We can calculate I. That is equal to pi over, was it 4 or 2?
4.
Pi over 4 times r to the 4th. And that radius is 0.02. And that is 1.257 times 10 to the minus 7 meters to the 4th. Q, so we need to calculate the centroid of this upper half. and then calculate this distance. The area is pi r squared over 2. That's the shaded area. So that is 6.283 times 10 to the minus 4.
Pokeball.
Kids today. And then the centroid of a semicircle, I believe, is 4 pi over 3r. Oh boy, I better look that up.
Centroid of a semicircle.
Some common knowledge.
4r over 3 pi.
No! I did it again. 4r over 3 pi. Okay, so 4 times 0.02 divided by 3 divided by pi. Up 4 times. And I got 0.008488 meters. And so Q is those two multiplied together. Which is 5.3 repeating times 10 to the minus 6 meters cubed. B is the diameter. So that's 0.04, 2 times the radius. And so tau x, y is equal to negative. Our V at the wall is positive 7,500. Q is 5.3 repeating times 10 to the minus 6. I is 1.257 times 10 to the minus 7. B is 0.04. And that is negative 7.96 times 10 to the 6 pascals. And so the stress tensor due to the shear force, well, this is the stress tensor for any points on the neutral axis, because all there is stress due to shear force, is 0, negative 7.96, 0, negative 7.96, 0, This is in megapascals. And the question asks for the absolute value, greatest absolute value of normal stress. Oh, in the x direction. Okay. So all the stuff we just did, we don't need for this question. This is specifically asking for what's happening in the x direction, which I was thinking the greatest absolute value of normal stress overall, which meant we had to come up with principal stresses. Are you with me on that? We don't, though. We just have to calculate all the things, bless you, that produce normal stresses in the x direction and see what the biggest is. Okay? None of this was relevant. What is relevant, though, is now the bending moment, the stress due to bending moment is always biggest when you're as far from the neutral axis as you can be. So this is at the top and the bottom in the case of something symmetric, where the height is the same above and below. So we are going to use sigma xx is equal to negative my over I. And our bending moment is negative 7,500. Our y, since we're looking for an absolute value, it doesn't matter which one we use. What is the biggest value of y that you can get on this cross-section?
0.02.
0.02, yep. You start at the neutral axis and go either up or down. So this is plus or minus 0.02. I'll choose the positive, just keep everything positive. And then our I, well, we did calculate that. That was good. 1.257 times 10 to the minus 7. Holy moly. 1.193 times 10 to the 9 pascals. That thing's coming down. You do not want to be out there.
So is that would we have to use the parallel axis theorem to get I at the very top edge?
No, that just like the mass moment of inertia, I represents the whole thing. So the mass moment of inertia represents a whole rigid body. The area moment of inertia represents a whole cross section. What we use the parallel axis theorem for is if we have a funky thing like this, the centroid is, say, over here somewhere. We break this up into pieces. The formula for the area moment of inertia gives us each one of these about their own centroid. And then we use the parallel axis theorem to calculate each one of those about that true centroid. Any other questions? Okay, well, we figured out something relevant here. I mean, somebody asked us if this is going to work. There's no way to make this work. You know, there's some stuff we couldn't figure out, but we figured out something meaningful there.
So is that still a valid calculation, even though we can't calculate the stress due to shear force?
Yeah, so yes, it is in this case because we found a point on this where the stress is at least this, you know. And so we found a point where we know it's going to break. It's possible that there are shear stresses that would make the situation even a little bit worse. It wouldn't make it too much worse because it's at the top and bottom and the shear stresses would be smallish, but one thing what do the normal stresses due to bending and shear force look like along a cross section? Remember Joy? This will always make me think of Joy now. Remember the girl Joy from Thermo? No?
Yes.
Okay. Well, anyways. Okay, so here is what...
What does that mean?
Okay, because I'll tell you why. But, so here is a side view of a beam. Okay? And let's say we make the cut here. The XX stress absolute value due to the bending moment looks like this. It's 0 at the neutral axis, and it changes linearly as you go away from the neutral axis. So think of this as okay, so it's 0 at the neutral axis, and the biggest is at the top and the bottom.
What exactly are we looking at here?
The lengths of those vectors are the absolute value
Well, like
of
this-
the
but
normal
like this-
stress.
It's like a distributed load.
Yeah, no. But like
Yeah.
the cut itself, like what angle are we looking at?
Yeah,
this?
we're looking from the side.
It's just like the right end of a beam.
Yeah,
Okay,
or
yeah.
really it's maybe the middle somewhere. Okay.
Oh yeah, because they're just multiplied by that y term.
Right. That's why it's linear, correct. Exactly.
Technically, one set of those arrows would be facing the other direction.
Yeah, that's why I did the absolute value,
Oh.
exactly.
I-
Okay, so now this is, I really don't think there's any other way to draw this, but Joy pointed out that I should always feel self-conscious whenever I draw this, because the profile for shear stress due to shear force looks like this. And I had never thought about it before, but she like totally cracked up in class about that. And now I can't unsee it.
It's a missile, right?
Yeah, exactly. But this is not a linear function. This is the absolute value of the shear stress due to the shear force. And it's biggest at the neutral axis and then decreases in a well-behaved thing like a rectangle, it decreases to 0 at the edges. Okay. So I don't know, that's helpful to, keep in mind as you work through this stuff. Where are we at? Do we have time for another one? Let's do another one. And then I also assigned number 1, I think, in the next set. Okay, so we want to calculate the internal loads for this, and then an expression for the stress tensors along the neutral axis as a function of x. Okay, this is a good one. Along the neutral axis means that the bending moment isn't going to matter. We have to first start by calculating those internal loads. The weight is 10,000 newtons. That acts here. We also have RB here and an RA here. And then we have this 15,000 Newton force here. So Newton's second law says RAX, RAY plus 0 RB plus 0 negative 10,000 plus, let's see, so that is 30 degrees. So this is negative 12,990.4 and negative 7,500. And this is equal to zeros. And then the moment equation, I'll do it about the left end point. So we have negative 0.7 times 10,000 plus 0.7 RB. And then only the Y component of this 15,000 Newton force produces a moment that is going to be a clockwise rotation. The moment arm is 1.4. The magnitude is 7,500. And this is equal to 0. So RB is I get 25,000. And then RA plus 25,000 is equal to 17,500. So RA is negative 7,500. That is RAY. And RAX is positive 12,990. So we have RA is 12,990.4. And then negative 7,500. And RB is 25,000. And we have to do 2 cuts here. Cut 1 is for x's between 0 and 0.7. We have a force over here of 12,990.4, negative 7,500. We haven't gotten to RB yet. The total weight is 10,000, and that's divided over 1.4. So that's a distributed load of 7,142.86 newtons per meter. And so now I can redraw this, and that weight force is at the middle, and it has a magnitude of 7142.86x. So Newton's second law says 12,990.4 negative 7,500 plus 0 negative 7142.86x plus t negative v is equal to zeros. So we have an internal tension of negative 12,990.4, so that's an internal compression. And then V is equal to negative 7142.86x minus 7,500. And the problem asks you to calculate M2. But remember, this won't come into the stress because we're doing it along the neutral axis. So let's just do the, I don't know how much we can do here, but let's think at least a little about the stresses on this half. So stresses for cut 1 along the neutral axis. First, the stress due to internal tension compression is T over A, which is negative 12,990.4 divided by the radius is 0.02 again, so divided by pi times 0.02 squared. And you get negative 1.034 times 10 to the 7 pascals. So for every x value, the stress tensor due to internal tension everywhere on the cross section, including the neutral axis, is negative. I'll write it as negative 10.34 in megapascals. Then the next one we usually think about is bending moment. There's no stress along the neutral axis. So then the last one we have to deal with is shear force. And that's going to be a tau xy. And it's equal to negative VQ over IB. I is equal to, well, we already did these for this same dimension on the last one, so yay. Our I is 1.257 times 10 to the minus 7. That's meters to the fourth. Our Q is 5.3 repeating times 10 to the minus 6. And so our tau xy is equal to negative of our shear force function, and that was x minus 7,500. Yep. Times 5.3 repeating times 10 to the minus 6 divided by 1.257 times 10 to the minus 7 divided by B, which is the diameter. And so you can write this as, so 5.
Wouldn't it be easier to figure out which X value would give us the greatest shear stress before doing this?
Well, in this one, it just asks to give it as a function of x.
Oh, that's right.
So we have 7140, no. We have 7.577 times 10 to the 6 x plus 7.96 times 10 to the 6. And so if you wanted to write that as a tensor, you could write it as negative 10.34. And then here you have 7.577x plus 7.96, 0, symmetry. And this is in megapascals. And that's the first cut, and you have to do the same thing on the other half. And you can see from this that on this cut, that shear force is going to get bigger as you get closer to the boundary, like as the X gets bigger. So you could plug in 0.7 and see the biggest value that you'd get on this first cut. Okay, any questions? All right, that's all.